Okay, how was the weekend? Terrible?
Weekend was good. Yeah, the quizzes.
Did the quiz keep you from going to Bullwinkle or something?
No.
20 minutes on those quizzes was a bit harsh.
Yeah.
It wasn't so much the math was hard, it was finding which button to click. And then fitting it all in 20 minutes. Oh, no.
Yeah, it would have been, if it was 20 minutes to write it, it would have been sufficient. To find the location of everybody.
You think half an hour would do it better?
Yeah, half hour would be sufficient. Yeah.
Okay, I tell you what, I will take that into account when I grade, and also from next time I'll give you more time.
Thank you.
Okay. If you had trouble with the quiz, like some other ways, you should. I think some of you had trouble with your browser or something. If you had some problems, did you say just you had trouble going up, scroll up?
No, I missed the button. I typed something that would go back and forth.
Oh, so then you have to go down again? Okay, what I'm going to do then is make it one problem at a time. You know what I mean? Like, it's just going to show you one problem at a time instead of showing you all the problems at once. I think that's going to help with that. Initially, maybe up to the second quiz, you might have some trouble, but then you won't have trouble because by then we will know what are the problems you're having with that. Okay? When I used Moodle last time, nobody told me about it. So, but again, sometimes they change Moodle from time to time, and then they change all the features sometimes, and it's hard to say. Okay. Did you guys have any questions from anything I said from last time? I want to write down your homework first. Section 1.5. You're looking at problems 1 through 15. The odd problems. 29 to 37. Also the odd ones. Even though I said just the odd ones from 29 to 37, if some of you feel like you need more practice, you should also go over the even ones. It's enough to do these ones, but if you feel like you need more examples and practices, that's even ones would be what you should do. Okay, so that's the homework from section 1.5. So let me see where we ended last time. So last time I only gave you some motivation examples, and the second motivation example was that what I said in the second motivation example was you have the number line, and then
are we supposed to be able to see this?
yes.
Sorry, I could be giving this lecture for 50 minutes without even looking back.
Okay. Okay, I said the problems that I assigned from section 1.5, the problems are 1 through 15, and 29 to 37 the odd ones. Okay. And yeah. So so last time, the second motivation example, I said, let's take the real number line, and let's say 0 is here, and let's say imagine a bug moving along this curve, and P of t is the position of the bug at time t, and the position of the bug at time t, let's say, is given by t squared. At time 1, then, the position of the bug will be given by 1, because 1 squared is 1. And then we wanted to know what's the instantaneous velocity at time 1, and the way we answered it is the following. We said that the average velocity over the interval of time from 1 to t, or t to 1, depending on whether t is bigger than 1 or less than 1, right? Either case, the average velocity will be given by this here. And so I am going to denote this average velocity by a of t. And the idea for instantaneous velocity is that, okay, I want to know what's the instantaneous velocity at time 1. Here I have at time t, I know the position at time 1. So what is the net displacement of the bug? That's position at time t minus the position at time 1 divided by the length of time. So that's the average velocity. Now the idea is that, well, let's compress the interval of time. That is, let's let t approach 1, and that means that you're shrinking the period. And as you shrink the period, you want to know what is happening to the average velocity. Okay? So once again, you know the average velocity from time 1 up to time t. Now you are compressing the period, so you're allowing t to approach 1, and you are looking at the average velocity. What is happening to that? Well, what's happening to the average velocity? Well, we know, we saw last time that this average velocity has graph given by this, where at time 1 you have a hole, and at time 1, what's the height of the graph? Why is that? Because the average velocity function, that's the same as t plus 1, right? Because t squared minus 1 factors out as t minus 1, t plus 1, right? So we know that this guy is the same as t plus 1 as long as t is not equal to 1, right? Then that's the equation. So the graph of this average velocity function is given by the straight line with the hole at 1. And now we see that as t approaches 1 from either side, the value of this average velocity function goes to 2. So that is, we are saying when t is close to 1, the value of the average velocity is close to 2. So my instantaneous velocity should be, so this should be the instantaneous velocity at time 1. So instantaneous velocity at time 1. And so we're saying when t is close to 1, the average velocity is close to 2. But the problem with that is that it's pretty. This is not a precise language. That is, what I need to address here is that how close can I make this average velocity function to 2? How close can it be made to 2? And that's where the definition of limit lies in. So because of this phenomenon that when t is close to 1, average velocity is close to 2, this phenomenon is expressed with this notation that the limit as the limit as t goes to 1 of the average velocity function t squared minus 1 over t minus 1 is equal to 2. So this phenomenon is expressed in this notation. Now, so what does it mean to write this? So what's the meaning of this? So what it means is that the value of this average velocity function, that is the value of this ratio, can be made as close to 2 as we desire by taking any t in an open interval centered at 1, except possibly equal to 1. So it means that I don't care what happens exactly at time 1. What happens if you look at the average velocity function, the ratio is undefined at 1. When t is 1, it's 0 over 0. So, but I don't care what's the value at exactly 1. What I care is when t is close to 1, what is happening to the function. And we are saying that the function gets closer and closer to 2 as t gets closer and closer to 1. Now, we are saying by taking any t in an open interval centered at 1, so what it means is that if I take a number line and another copy of the number line, and let's say the number 2 is right here, the number 1 is denoted here. So let's say one of you give me a very small number epsilon. Maybe epsilon is 0.001 or 0.0001, and you ask, can I make this ratio to be within epsilon of 2, within a very small number of 2? That's how much close I want this ratio to 2. Can I do that by taking any x? Can I do that by taking any x in a suitably small interval centered at 1? By taking any x in that interval except possibly 1. If I can do that, then the limit is 2, otherwise it's not. So it means that I have to be able to take x on either side of 1. Okay? So that's what it means to say that the instantaneous velocity is 2. Okay? Now, of course, in this course, we don't just care about the velocity or something. We want to work with the general function, right? So let me just write down the limit for a general function. So when we write the limit as x going to a of f of x is equal to L. When we are writing this symbol, there are some assumptions here. L is a number. Okay, I'm assuming L is a number. it's not something else. Okay, and we are assuming f of x may not be defined at a. When I'm writing this symbol, f of x may not be defined at a. However, f of x is defined in an interval centered at a. Am I making sense? It may not be defined at a, but it is defined in some open interval centered at a. And so then what does it mean to say that this limit is L? The limit. So how do I say it? I say that the limit of f of x as x approaches a. The limit of f of x as x approaches a. And that's L. And what does it mean to say that? Again, it means the same as before. F of x can be made as close to L as we desire by taking any x in a suitably small interval centered at A, except possibly equal to A. Okay, so again, this has similar meaning as what we did before. Maybe I'm doing this redundant, but I'm going to do it again. So this is one number line, this is another number line. What we are saying here, if this number here is L, this number here is A, we are saying that the question that we are asking, can I make f of x to be within any specified number I want to? That is, if you give me a very small tiny number epsilon, can I make the value of f of x to be within epsilon of L? So I want f of x to be within epsilon of L. Can I do that by taking any x in an open interval centered at A, except possibly at A? By taking any x there, can I do that? Okay, if I can, then that's the limit. Otherwise, it's not the limit. Okay, so that's well and good, but I'm pretty sure this definition doesn't make complete sense until you go over some examples. So let's go over some examples. So example number 1. Let's say I have the function f of x to be x squared, and what I'm considering here then is what's the limit of this function as x goes to 2, let's say. Well, and many of you, I know that you have already taken calculus. You know this limit is. Sometimes I find it hard to explain something to someone who already have seen something before, because you have this idea already in your head, and because you already know it, you really don't want to listen to what I'm saying. Okay, but if you have taken calculus before already, it's a good idea to sometimes to tell yourself that you don't know anything about it, okay, and sort of try to not remember anything from calculus that you have done before. Then my discussion will make more sense. So here, again, we don't know any of the limit rules. So if you're trying to use the limit rules at this point, you're not allowed to use the limit rules, but you'll be allowed to use it as soon as we do them. But at this point, I'm trying to study what is the limit of this function, and we will study the graph of this function to come up with this. So let's say here we have the graph of this function, and the graph of this function, well, we all know how it's a parabola. So, and it has another side to it. And let's say here is the number 2, and the height of the graph at 2 would be what? 4, right? So what do I see? I see that as x approaches 2 from either side, right? So the question I want to ask, can I make the value of x squared as close to 4 as I want to by taking any x in a sufficiently small interval centered at 2? And in this case, the answer is yes. I mean, if I want to make my function within this much of 4, within this much of 4, can I do that? Well, yeah. If I take any x, if I take any x in between here and here, right, I will accomplish that. Okay, so yes, I can make the value of this function as close to 4 as I want to by taking any x sufficiently close to 2 on either side of 2. Okay, so this limit is 4. It's sort of obvious from the graph. It's got to be 4. Let's look at another example. Did that make sense? Okay, let's look at another example, which is where I want to make just one more point. Let's take the function f of x, which is x squared minus 1 over x minus 1, and this is when x is not 1. Otherwise, the value of the function is 4. That is, when x is exactly 1, I am saying that the value of this function is 4. So, what's the graph? The graph of this function is going to be a straight line, right? Like this. Let's say here is 1. Here is 1. What is the height here? You remember what the height here? 2, right? We saw that the height of this graph. So the graph of just x squared minus 1 over x minus 1 is the straight line with the hole at 1. But what's the graph of this piecewise function? What's the point on the graph corresponding to 1? Well, the value of the function at 1 is what? 4. Right? When x is 1, the value is 4. When x is not 1, then you use the other formula, right? So the value of the function at 1 is in fact 4. So this point is on the graph, right? So what's the graph? The line with the hole at 1, but then you have the point which is separate from the line. That's the graph, together with that point, single point. Now, if I ask you the same question now, what is the limit of this function? What's the limit of this piecewise function as x goes to 1? It is 2, but some of you might be tempted to say 4, right? Because the value of the function at 1 is 4, but the limit is in fact 2. It's not 4, even though the value is 4. Remember what I said? We don't care what's the value of the function at 1 is. We care what is happening to the function when x is near 1, not equal to 1. And you can see that, 4 couldn't be the limit, because that would mean that I can make the value of the function as close to 4 as I desire by taking any x in a very small, tiny interval centered at 1, right? But when I take very tiny interval centered at 1, the value of the function is actually getting closer and closer to 2, right? So the limit is 2, not 4. My point in this example was to make sure that you see that the limit is not the value of the function at 1. The limit is different. It's 2. It's not 4. Even though the value of the function, that is, even though f of 1 is 4, the limit at 1 is not 4. Okay? That's the point I want to make. Is that making sense? Okay. Here's an example where the limit doesn't exist, right? I want to show you one example where the limit doesn't exist. And that example is, again, let me take a piecewise function where f of x is x squared if x is larger than 1, and x plus 1 if x is less than 1. And what's the graph of this guy? Well, I think we know the graph of this guy very well because we have seen these things before. The graph is given by let me make a change here. I want this to be the other way. I want this to be less than, and I want this to be greater than 1. So what's the graph? Well, the graph, when x is less than 1, so let's say here is 1, and here is the point 1, 1, okay? What's the graph of the parabola between on the left side of 1? Well, it's this, right? That's the graph of the parabola on the left side of 1. And what's the graph of the x plus 1? The graph of x plus 1, when x is 1, the value is here. So this is 1. This is 2. Would you agree that the graph is given by a line like this for x plus 1? Okay. So again, I discussed how to draw this type of functions before. You draw each part separately, right? You draw each part separately, and then you delete the part of the parabola on the right side of 1, and you delete the part of the line on the left side of 1, right? In order to come up with this. Okay, once you have come up with the graph, then now we are asking the same question: what's the limit at 1? So what is the limit? What is the limit as x going to 1 of f of x here? Well, I mean, there seems like two possibilities, either 2 or 1, right? But either one doesn't work. The question you want to ask is that, can I make the value of this function as close to some number? If you say that the limit is L, then you have to show that I can make the value of this function as close to L as I want to by taking any x in an interval centered at 1, right? By taking any x there. But if you take any x there, sometimes you are close to 2, sometimes you are close to 1, right? So you can make this function arbitrarily close to 2 by taking x on the right side of 2, right? You can make this function arbitrarily close to 1 by taking x only on the left side of 1. But I want to know what happens as x gets to 1 from either side, and we see that this limit can't possibly exist. So you cannot give me a single number such that this function approaches that number as x approaches 1. So this guy does not exist. Is everybody okay with that? Everybody is okay? Here's a little bit different example. You probably, if you have taken calculus before, most probably you haven't seen an example like this. Suppose I have f of x, which is defined by 1 if x is an irrational number, and let's say it is 0 else. Else means that when will this be 0? Well, when x is rational. When x is rational, it will be 0. Otherwise, it's 1. What's the graph? Can I draw the graph? Well, I cannot draw the graph. Okay. However, I can sort of give you some idea how the graph looks like. Okay. So here are our x and y axis, let's say. And the graph basically is the following. Let's say this line here is the height 1, okay? So this is the graph of y equals to 1. This is at height 1. So what happens is that whenever x is irrational, what's the height of the graph? 1. So whenever you have an irrational number, the height of the graph is on this. You get a point on this line, right? Whenever x is irrational, you get a point on this line, and but whenever x is rational, you get a point on the x-axis, right? So then you get just points on the x-axis like this. So the graph has points on the x-axis and also points on that line, depending on whether x is rational or irrational. So if I now ask you, hey, what's the limit as x goes to 3 of f of x? What did you say? Is the limit 1 at 3 or 0 at 3? What is it? So let's say the number 3 is here. Because the number 3 is a rational number, right? It'll be, say, let's say this is 3, right? Let's say this is 3. Because it's a rational number, the point corresponding to that would be on the x-axis, because the value would be 0 at 3. We are asking, what's the limit at 3? Is it 0? Is it 1? It doesn't exist, in fact, right? Why is that? Well, no matter how small interval you pick around 3, there is always an irrational number there. There will always be a rational number there. Am I making sense? No matter how small interval centered at 3 I pick, there will always be an irrational number. There will always be a rational number there. So sometimes it will be 1, sometimes it will be 0. Am I making sense? No matter how small you pick, the function could be close to 1 or 0. So the limit couldn't possibly exist. Am I making sense? Is that making sense? So this limit really doesn't exist. And in fact, the limit of f doesn't exist everywhere. So this is a function. This is a funny function. For this function, the limit doesn't exist anywhere. Am I making sense? Of course, that's a function, because you're saying f of x is. So you're saying f of x is 1 whenever x is irrational. F of x is 0 whenever x is rational. Okay. It's a function because every input has only exactly one output, right? So it is a valid function. But what I'm saying is that the limit of this function doesn't exist at any point. Okay? Okay, so this is one of those weird functions with that quality. Okay. Here is another example that you might not also see before, even if you have taken calculus. Something like this. What's the limit as x goes to 0 of sine of 1 over x? What is that limit? Can someone tell me why that is? What is that limit? What's the limit of this function? Yeah. Why? Okay, remember, what you're saying is that the limit doesn't exist, which is correct. However, your reasoning is wrong. Okay? I was hoping that somebody will give me that reasoning so that I can, make a drama about it so that you can remember it. Okay? So, the function is undefined at 0, which is correct as well. But remember, I said when we are talking about limit at a point, We don't care what happens at 0. The function is defined or not defined, doesn't matter. Okay? This function, the limit doesn't exist, but that's not because it's undefined at 0. Remember we had this example, right? Where is it? Here. Remember, even if this point is not there, right? The function would be undefined at 1, right? But the limit still exists at 1. So the limit doesn't exist. By why is that the case really? Well, here is why. And again, these are the types of examples that I wouldn't usually ask in an exam, but this sort of clarifies the definition of limit. So what's the graph of this guy? Can I sort of tell you how the graph looks like for this guy? And I can. And I'll then explain why the graph looks like the way it does. Let's say here is height 1. And let's say here is height -1. Well, one thing is for sure, right? That the graph of this function would be between -1 and 1. Would you agree with that? Because sine function always has values between -1 and 1. It cannot be outside of that. So I know that the graph is in between. So how does it look like? Well, in fact, the way it looks like is the following. It sort of looks like this. So it's sort of, I have a very I have difficulty drawing it, but the idea is that it oscillates like this. As x gets closer and closer to 0, it oscillates more. Okay. However, the function is undefined at 0. It's never going to touch y-axis. Okay. But it's going to keep doing this. Okay. And how do I know that? Here's why I know that. Suppose you give me any number. Let's say you give me a value of x, right? You give me, let's say, a very small x. So x positive and small. No matter how small number you give me. Very, very small. So let's say x is somewhere in a very small interval centered at 0. You gave me very small number. So, but would you agree that I can always find a really large value of n? N is a integer, so I can find a very large integer n. And so if I look at 1 over 2 and pi, would you agree that I can make it smaller than x? You give me any x, fixed x, I can find a very large integer n, right? So that 1 over 2 and pi is smaller than x. You think I could do that? Well, if x is 0.001, right, I can just take n to be 1,000. Would that do it? Yeah, because 1 over 1,000 is already 0.01, and I'm multiplying by 2 pi also. So that's why I'm saying no matter what x you give me, I can find a large integer so that 1 over 2 and pi is smaller than x. Now, think about what's happening to this function. What's the value of 1 over sine of 1 over x? What is that when x is equal to this number? What's the value of this function? Well, what is 1 over x if x is this guy? If x is this guy, right, what would that imply for 1 over x? 1 over x would be what? 2 and pi, right? Right? What is sine of 2 and pi? What is sine of 2 and pi? 0. It's a multiple of 2 pi, so it's always on the positive x-axis. So if the terminal side of the angle is on the positive x-axis, then sine is 0, right? So this guy would be 0. Am I making sense? So what I'm saying is that no matter how small interval centered at 0 you pick, I can always find a number there where the sine value is 0. Is that what I showed? No matter how small interval centered at 0 you give me, I can always find a number like 1 over 2 and pi there, right? So that sine of that number is 0. So I'm saying I can always do that. Also, notice that instead of picking 2 and pi, I could also pick 1 over 2n plus 1 multiplied by pi over 2, right? I can pick n so big that I can make this guy also small, very, very small. So in that case, what's the value of this function? What is sine of 1 over x when x is this value? What is that? What is that? When x is this, 1 over x is what? It's just 2n plus 1 times pi over 2, right? See, if 1 over x is that, then what is this guy? So basically you're applying the sine function to an angle which is an odd multiple of pi over 2. Odd multiple of pi over 2, what's the terminal side? Odd multiple of pi over 2, like pi over 2, 3 pi over 2, 5 pi over 2, is either on the positive y-axis or the negative y-axis, right? What are the values of sine? Plus or minus 1, right? So notice what I'm saying then. I'm saying no matter how small interval I pick around 0, there is always a value where sine value is 1. There is always a value where sine value would be negative 1. There is also a value where sine value is 0, right? Does that prove that the graph would be vibrating all the time as you go nearer and nearer and 0? Which would mean that the value of the function is not approaching a single number, which would mean that the limit doesn't exist. Is that making sense? So the answer why the limit doesn't exist is more complicated than just saying that it is undefined at 0. So here's what we can say. The limit does not exist. Okay? Is everybody okay? Again, I'm not going to ask you to do similar analysis to come up with limits like this in the exams or even in the homeworks, okay? But I think this example clarifies the definition of limit more than any other examples. Is everybody okay? All right. What I want to do, in fact, go back to one of the examples that we did. This one. Notice that we said the limit at 1 did not exist. However, in such situations, we are going to say the following. However, we are going to write that the limit as x going to 1 from the right side, okay, is going to be 2, yes, and the limit as x going to 1 from the left side of 1 is 1. So what does it mean to say that the limit of f as x goes to 1 from the right side of 1 is 2? Well, it means that as x gets closer and closer to 1 from the right side of 1, the value of the function is getting closer and closer to 2. More precisely, we want to say that I can make the value of f as close to 2 as I want by taking any x sufficiently close to 1 on the right side of 1. Am I making sense? So in this problem, when I'm writing this, what does it mean? It means that, again, if you don't mind, I'm going to take 2 number line again. What did I do? Oh boy. I did something and I changed the note, so maybe I should go to not the full page, give me the normal page, and then I have to go back here. Yeah. Full page. Okay, so drawing. Okay, so here's what's the meaning of this limit? It means that here's the number 2, here is the number 1. Can I make the value of this function to be within any small distance from 2 by taking any x where? By taking any x in a sufficiently small interval like this. So it's an interval where 1 is the left-hand point. It's an open interval where 1 is the left-hand point. By taking any x, can I make f of x to be close to 2? And if I can, then that limit is 2. Is that making sense? I can make f of x as close to 2 as I want by taking any x sufficiently close to 1 on the right side of 1. Okay? If I could do that, then that limit is 2. What's the meaning of the other one? Very similar, right? Very, very similar. So I'm going to write down the meaning again, just to have it on my notes. So for any function, when we have that the limit as x going to a from the right side, so this is how we say it. The limit of f of x as x goes to a from the right side of a is L. Sometimes you say that the right-hand limit of f at a is L. Okay, so what does it mean? It means f of x can be made as close to L as we desire by taking any x sufficiently, let me just say it this way, sufficiently close to a on the right side of a, right side of a, again except possibly equal to a. Again, that means that I don't care what happens at a. All I care what's happening when x is close to a on the right side of a. Okay? The meaning of the other left-hand limit is similar. I'm not going to write it down. The meaning of the limit x going to a from the left side of f of x has equals to L. So this has a similar meaning. And let me just give you one example. So I'm not giving you your time back today. If I ask you what's the limit of root of x minus 2 as x goes to 2, what did you say? What's the graph of this guy? It's a parabola that opens, it's the upper part of the parabola opening to the right. Vertex at 2, that's the graph. If I ask you what is this limit, what did you say? You will say it doesn't exist for now because I'm saying without plus or minus. If I ask you what's the limit from the left, you would say it doesn't exist. But if I ask you what's the limit from the right, that would be 0. Okay? Is everybody okay with that? Now, before you leave, though, I want to inform you that in Moodle I have a secret lecture 10, part 1 and 2, which I never really gave in the class. So what are they? They are on more examples on trigonometry review, and also the graphs of trig functions. So if you forgot the graphs of trig functions, you should look at them. It's about 1 hour, and you can review that. Okay. All right. I'll see you on Wednesday.
You guys want to plan a party and get together and watch?